record. So we'll finish 3-4 today, and then we will start 11-1 and 11-2. These due dates have to change though. So 11-1 and 11-2. Let's see, instead of the 30th, let's change that to the following Monday. This one as well. All right, so 11-1 and 11-2, I'll extend those. Okay. Let's see, what about these weekly uploads? Because I know the weekly uploads is like the written work, right? So the 3-1 through 3-3, I'll leave that. This 3-4 through 11-2. See what the due date is for these guided notes. See if I need to change those as well. Supposed to have these. They wanted me to have these due on Sundays, so these are still due on the 5th, so those should be good. The written notes and the guided notes. Okay, so I'll leave those alone. That's everything that y'all have due, right? All your homework and stuff. So, again, on your syllabus, you could scroll down, and then we kind of have a schedule here. So we're a little bit behind. We'll eventually catch up. Here's the book. So let's see. 3-4. Since chapter 3's review, we covered most of 3-4. Just gonna skip the rest and go into chapter 11. Okay. So we don't get too far behind. We need 11-1 and 11-2. We're going to start calculus now. With limits. Limit. Make that a little bigger. Maybe that's too big. Let's see. Oh. Due dates for 3.4, 11-1, and 11-2 in my math lab extended. I forgot what it was. The 6. Guided notes and written notes, right? Still due on the 5th. They really should be in sync, right? So I'll try to keep those in sync because the written notes go with my math lab, right? But I already changed it. I don't want to change it again. So I'll try to keep things in sync so they're due on Sunday nights. If we can get everything in sync, that would be cool, right? But stuff to remember. These will be the following Sunday, right? On the 6th, because we're not going to get through both 11-2, 11-1, and 11-2 today, right? We might get through 11-1. But we do need to catch up. I'm supposed to keep y'all in sync with all the other business calculus classes, right? So starting 7.1 today. Right, by the end of this class, I'll know everything about this class. And now after that, I'll teach 3 other subjects. By the time I get back here Monday morning, I'll be like, what section are we in? Right? Dude, I used to teach just the same class over and over though before, right? All right, let's look at an example here. limits. Limits is how we divide by zero, basically. That's what calculus is. Calculus is algebra where we can divide by zero. So what we do is instead of dividing exactly by zero, we just look at what happens really, really, really close to zero. And then we can do that with anything else. So let's look at this function here, right? Obviously, you can't plug the number 2 in here, right? If you plug in the number 2, you're dividing by zero, right? So what we'll do is we'll look at what happens if you plug in values that get really, really, really close to zero. And they have this nice little chart here for us. So let's see. So here's numbers that are less than 2, but getting closer and closer to 2. So you can see the output here, right? At 1.9, we get a 4.8. We get a little closer to 2. We got a 4.98. We get a little bit closer to 2. Notice this is getting closer to 5, right? And then if we look at numbers that are bigger than 2, right, but getting closer and closer, you can see the output is getting closer and closer to 5. So what we would say is that the limit as x approaches 2 of this thing is 5, right? So for this particular example, it doesn't matter if you're approaching from the left or from the right, you're getting the same output, 5, right? So even though you can't plug in a 2, the limit exists, right? Now there's going to be examples where if you approach it from the left, you might get one number. And if you approach it from the right, you might get a different number. So we might have to talk about like the limit from the left or from the right, because those might be different. If they're the same, we just say, well, the limit exists, and in this case, it's 5. Does that make sense for a general idea of what limits are? All right, and usually if you graph this thing, I hope they give us a picture of this graph. Here we go. Here's the graph. Some jargon here. So you can see this thing is really just a straight line, but there's a hole in it. I don't know if y'all can see that right here at 2. There's a hole in the graph, right? Yeah, zoom is fine. Yeah, if you're sick or whatever, yeah, zoom in and that's totally cool. No problems with that, okay? So, but this is like a rational function. It's a polynomial over a polynomial. The reason why is we could probably factor this. This is actually x minus 2 times something. I don't know. I could factor it, but I don't want to. But that's what the top actually looks like. So you could like get rid of that, and then this is just a line, what's left over. That's why this is just a line. But when you write it like this, since these are equal, they're equal everywhere except for when x is 2. Whenever I do this and get rid of that, right, this guy's defined everywhere, but this guy is not defined for x equals 2, but it's defined everywhere else. So this guy is this straight line, but there's a hole in it, is the way it's been written, right? So if I wrote something like x minus, or another example, times an x minus 1 over x minus 2, right? This is a straight line with a hole in it at x equals 2, right? Because I could do this, right? So this is x minus 1, assuming x is not equal to. These are equal for every value of x except for x equals 2. For this guy, it's not defined at x equals 2, but everywhere else, these are the same thing. Right? So that's what you're seeing right here. So the limit, if you approach it from the left, you're getting 5. If you approach it from the right, you're getting 5. So we'd say that the limit as x approaches 2 of f of x is equal to 5. And in these next few sections, as we're doing limits a lot, you might get sloppy. Try not to get sloppy. It gets annoying to have to write the limit of x approaches. You're going to end up writing that a whole lot, you know. But if you don't write that, then it's technically not correct. Okay, that's going to pop up and get in the way every time. It's okay. Here's your happy rectangle of important information, right? This is just defining what a limit is. So They talk about the limit as x approaches a, just to be generic, okay? And then they call the limit L, so that's the generic letters they like to use here. And they're just saying that if the limit's the same from the left and from the right, then the limit exists, and generically we'll call it L in here. Let's look at another example. This one's a technology example. So here's a function f of x. This is a simple polynomial, right? And remember, polynomials, they're continuous, right? They look like that. The higher the power of x, the more wiggles you get. But they go forever left and right. There's no hole in the middle. It doesn't do like, there's no like vertical asymptote or anything. Polynomials are just pretty continuous, right? Continuous functions, all right? So for something as simple as a polynomial, to find the limit, all you really have to do is plug in the number. So like the limit as x approaches 3, it's just going to be f of 3. You just plug it in. So like something like this. Here's 3. You just plug the 3 in and see what you get, right? So limits get, this is the simple functions. It's easy to do limits. You just plug the number in for x. That's what it's going to be, right? It gets weird when you have stuff with like this, with a hole in it, or if you have like vertical asymptotes. You might have something like it veers off this way and veers off that way. So if you're approaching this number, whatever a, if you're approaching it from the left, you get positive infinity. If you approach it from the right, you're going to get negative infinity, right? So we'll look at these kinds of examples probably in the next section. And they do the whole chart right here, right? Basically, for this example, if you plug in a 3 here, you're getting what? 3 squared is 9, plus 3 is 12, plus 1 is 13. Right, all you have to do is plug it in. And they're showing that the values, as you get closer to 3, the output gets closer and closer to 13. This is a simple example. It's a simple case. All right. And again, for any of your homework and stuff, have a graphing program like ready to roll. I mean, whether it asks you to or not, but like when I'm doing that, it's like the first thing I do is I just graph this in software, because that visual aid is going to help immensely, right? So you can just look at the graph usually and tell what the answer is, right? And here you go, the graphical method. And it's good to graph this, any function you see, because then you'll get used to when you see a function, eventually you'll get that intuition where you just kind of intuitively know roughly what it looks like in your head. So this guy, remember the number E, all right? E is Euler's number, and it's 2.7 something, right? It's a transcendental number, all right? The decimal goes on forever with no pattern, all right? It's our natural base, okay? And we're gonna see E is awesome, all right? When we start getting rates of change, we're gonna see that like E to the X, when you graph it, it looks like this. It's the one function who the slope right here, whatever that slope is for that point, it's whatever this value is here, right? It is basically, it is its own slope. So it's like the number 1 of calculus, if you will. Like 0 is the identity for addition. You add 0, nothing happens. 1 is the identity for multiplication. You multiply by 1 and nothing happens, right? Well, e to the x is the identity for calculus. And it is its own rate of change, because that's what calculus is really all about. All right, so this guy, let's see, you can see, let's see, when is this a problem? When would this be 0? If I plug in a 3 here, 3 minus 3 is 0, and e to the 0 is just 1, and 1 minus 1 is 0. So this thing is not defined. This guy's not defined for x equals 3, right? Because if you plug in a 3, you're getting 0 on the bottom. But look at this, you're also getting 0 on the top, right? 3 minus 3 is 0. So it's one thing to have like 3 divided by 0. That's definitely undefined, right? But in here, we're going to look at cases where you have like 0 over 0, right? So the goal here basically with stuff like this, sometimes the goal is to factor the 0 out, right? That's kind of what we did up here in This example, right? This guy right here. If you plug in a 2, you get a 0 on the bottom, but you also get a 0 on the top. So we factored out this x minus 2, so we get rid of that 0 over 0, and we ended up with a number. Okay, so let's see what, we don't have the mechanics to actually figure out what this limit is, except by the graphical method, right? And in a higher level class, you'd be able to take that and rewrite it as a polynomial, but it's a polynomial that never ends, right? So y'all don't know how to deal with infinite sums yet, right? It's a nice math trick. Okay? So here they just want us to graph it and look at the picture. Here's the picture. Is it on the next page? I mean, you can plug in numbers, right? You don't have to have the graph. You could just plug in numbers closer and closer to 3 and see what's coming out. Where's their graph? Is this it? I guess I can use my graphing software. It's let me get rid of this. Okay, I guess that crappy. I mean, I don't know why they do stuff like this over here. Like, this is the best graph they could come up with. Right? Like, this is the worst graph. Out of all the software in the world they could use to produce the graph, they use a graphing calculator snapshot, right? The worst math utility tool we have, right? But anyhow, this is what it looks like, the graph of it. And you can see that right here at 3, there's a hole in the graph, all right? So if you could see the whole picture, like if they had a real actual piece of software, you would just look over here and see what this y value is. Apparently, they're telling us it's 1. Okay, so you could graph it and then look at it and be like, okay, if I'm getting closer to 3, the y value is getting closer and closer to 1. Okay, and so that's your graphical method. Graph it and then look at it, right? Or you could do the numerical method where you plug in numbers closer and closer to 3. Like you plug in 2.9999, see what you get, and you plug in 3.000001, plug those numbers in for x, and see what they're close to. Okay, you might want to plug in more numbers. For something that's a straight line, you could just plug in a couple of them, but some functions are like, they might look like this. They might be all like weird. So you might need, for the numerical method, you might need to plug in more numbers like, 2.998 or whatever, just to see where it's going. So we're going to be focused on the analytical method where we actually rearrange this thing. We'll factor stuff out to where we can actually get the actual result. That'll be the analytical method. Graphical or numerical, these kind of suck. It's what you do when you don't have the actual mathematical tools you need to precisely show what the answer is. Like these are kind of guesstimations, right? You're looking at a picture and going, it's roughly 1, right? It might not be 1. It could be like 0.999, right? Those aren't the same thing. They're real close. So these give you something that's close enough, right? But we need the tools to get exact answers when possible. Example here. All right, find the limit as x approaches 4 of f of x, where f is the function whose rule is. So this is a step function, kind of. Well, so f of x, the function is 0 if it's an integer. So you could see, like for the number 1, if you plug in 1, you get 0. If you plug in 2, you get 0. If you plug in 3, you get 0. But any other value of x, they say it's equal to 1. So you're getting this line with holes in it. So instead of here, you got down here. So that's a weird, awkward function, right? But I mean, it is a function. They want to know what happens when x approaches 4. So let's look at 4 here. Here's 4. If I'm approaching from the left versus approaching from the right, we're going to get the value of 1. See, I'm up here at 1, I'm up here at 1, I'm up here at 1. Over here, I'm up here at 1. I'm 1 all the way except for right at 4. See, f of 4, because 4 is an integer, is equal to 0. But if I'm looking at the limits, right, this 1 point doesn't matter. The 1 point right at 4 doesn't matter. Okay, I'm up here at 1 the whole time. So even though f of 4 is 0, the limit of f of x as x approaches 4 is going to be 1. Because everything is up here at 1, right? Except for this 1 point. Just kind of like back to this thing where there was a hole in it, right? What happened right at the number 2? It was totally undefined, right? But when we're looking at the limits, we don't care about what happens exactly at 2. We care about where this thing is headed. This thing was headed for 5. It's totally undefined at x equals 2. But when you go to 2, if you go to 2, this guy is going to 5. This guy, as you're approaching 4, right, the function is approaching the value 1. It just so happens that instead of being undefined at 4, it happens to be defined to be 0. And so it's with limits, it's not about what happens right at that point, right? It's about what happens as you approach the point. Okay? All right. So when does the limit exist? Sometimes the function's not defined. That very first example we did, the function was not defined at x equals 2. But the limit can be defined, as we saw it was. All right. Sometimes, like a polynomial, all you have to do is plug in the value in for x, right? If it's a nice smooth thing with no holes in it, all you have to do is plug in the a into the x and evaluate. Okay? Here's what we want to be able to do. Find the limit algebraically. So again, you have to have your algebra down to be able to do calculus. Right? Algebraically. So we're going to assume that you know algebra. All right. Some of y'all are still having, some issues with algebra. By the end of this class, you should be masters of algebra and okay at calculus, right? Okay. I know it takes a lot of practice, It's all pattern recognition and stuff. So here's we're going to break it down and talk about the different possibilities. So remember your toolkit functions, which is your basic functions. They were like f of x equals some constant, f of x, the input is the same as its output, and we liked x squared, and we liked square root of x. These were like our basic functions, So we're going to look at the limits of these toolkit functions. So the limit of a constant function, remember a constant function, whatever it is, c, it's just a horizontal line. No matter what you plug in, you get the same thing back, right? So this thing is just a straight line. There's no holes in it or anything, right? So if I pick an a, just any value for x, the limit's always still going to just be c, all right? So something like if f of x is 2, no matter what, then, well, the limit as x approaches any number you want, the limit of this is still going to just be 2, right? Because this function is always 2. If I'm approaching this from the left or from the right, the output's going to be whatever that number is. In this case, I said 2 is what the function is. They call it d now, okay? Instead of c, they're going to call it d, whatever. The identity function, this is your f of x equals x. This is the function where whatever you plug in, the output is the same. So f of x equals x. This is the identity function. The output's the same as the input. Remember, if you graph this, it looks like this diagonal line, right? So let's pick any number you want, a, right? As x approaches a, f of x is approaching, well, a, right? So the limit, try that again. The limit as x approaches any number you want of f of x, and f of x is just x. In this case, all you have to do is plug in the a, because this is a simple, again, any function that doesn't have holes in it, that's continuous, all you have to do is plug this number in, right? That's it. Right? The only time the limits are anything other than that is when there's holes in your function or it goes shooting off to infinity or something. Properties of limits. Here's a huge paragraph of all kinds of nitty-gritty, but it's just simple stuff right here. Basically, it says the things that you want to do, you totally can do. So let's say you have two functions, f and g, right? So the limit of f exists as x approaches a, and the limit of g exists as x approaches a. All right. What they're saying here is that the limit of the sum, the limit of f plus g, is the same thing as the limit of f plus the limit of g, which is real convenient, right? The sum, the limit of the sum is the sum of the limit. And that's something you would want it to be, right? It makes things simple. And the same thing goes with the difference. The limit of the difference of the functions is the same as the difference of the limits. Okay? And same thing with the product. The limit of f times g is the same as the limit of f times the limit of g. And the same thing with dividing. The limit of f divided by g is the limit of f divided by the limit of g, assuming that the limit of g is not 0, because you can't divide by 0. And then the power property. The limit of f to the r is the same as the limit of f to the r. So you can either take f to the power and then take the limit, or you can take the limit of f and then raise that to the power. So all this thing here says is all the things that you feel like you should be able to do, you can do. So we'll see that, you know, this kind of stuff sinks in with examples more than a huge paragraph full of symbols, right? All right. This. So I'll write it out and then I'll copy in their nicely written stuff, just step by step. So here's a function. They want us to find the limit as x approaches 5 of f of x. The limit as x approaches 5 of f of x is equal to the limit as x approaches 5. So f of x is equal to this. So I'm just going to replace f of x with this. And I need to put the parentheses because I want to take the limit of all of this. Without the parentheses, I'd just be taking the limit of this and then adding 2x minus 9. That's not the same thing, okay? So because this is a polynomial, it's x squared. It looks like this, but it's been like moved and shifted, right? There's no holes in it. It's just a basic polynomial. So for this limit, all I need to do is plug the 5 in. So this is 4 times 5 squared plus 2 times 5 minus 9. This is whatever. I don't know, it's some number. You can plug it in your calculator, right? We're not here to do arithmetic. We want to learn calculus, right? That's it. Nice polynomial. The limit is simple. Let's see, they took like 400 steps to do this. Okay. They're citing each property. Let's see all their steps here. All right, here's the limit. And then they said, all right, that's what I wrote. Oh, okay. They break it up into little pieces. So they're saying, okay, from here to here, all they did was put parentheses around 2x minus 9, not sure why. But they're just saying that the limit of all this stuff is the same as the limit of, you can break it up into the limit of 4x squared plus the limit of the other part. Yeah, a giant waste of time, but to emphasize all the rules is what they're doing here. So I like the way I did it, right? You just plug the number in, right? That's intuition. But they want to break this into little pieces. They say, okay, you could think of this as a function and this is a function. They're saying this is the same as the limit as x approaches 5 of 4x squared plus the limit as x approaches 5 of 2x plus the limit as x approaches 5 of minus 9, right? The limit of the sum is the same as the sum of the limits. And then they say, okay, well, this is the same as the limit approaches 5 of 4 times the limit as x approaches 5 of x squared plus, and now this guy, they would say, this is the limit as x approaches 5 of 2 times the limit as x approaches 5 of x. And then we could say, okay, I'll pull the minus out, minus the limit as x approaches 5 of 9. And then this guy right here, they would say, okay, this is the same thing as if I took the limit and then squared that. And I think that's about as far as you could break it down. But this is the same thing as if you just plugged 5 in for the x. All of this, okay? So writing it all out like that, you don't have to do that. That's not necessary ever, okay? But if you have something that's not a pretty polynomial that might be jagged or have holes in it or something like that, you might want to do some of this stuff because it'll help you like finagle it and get a number out, okay? Does that make sense? All right. See right here, they're like, after all of that, they're like, yeah, oh, by the way, for this case, all you have to do is plug the 5 in. Boom. And they say, here's a polynomial of degree n. You can always do that. If it's a polynomial, it doesn't matter the degree. Just plug in the value in for x, and you're good to go. Let's look at this guy. What do they want? This is a polynomial. All you have to do, plug the 2 in. Okay. That's it, because this thing is continuous and there's no holes in it. When I say continuous, I mean there's no breaks in the graph. Okay. That's why we love polynomials. What do they do here? They have oh yeah, part B. So this one, this is a polynomial, this is a polynomial. If you multiply these two together, you still have a polynomial. So you could just plug the -1 in for x everywhere. Okay. They show, oh, you can do, instead of the limit of the product, you can do the product of the limits, right? In the end, you're still the same thing as just plugging the -1 in everywhere, okay? Again, polynomial times a polynomial gives you just another polynomial, right? There's no holes in that function, so you just plug it in. This stuff isn't too complicated. I mean, there's kids out there that discovered calculus on their own, like by the age of 12. Calculus isn't that deep. I mean, literally, there's 12-year-olds that have discovered calculus on their own with their own symbols and notation. Right? The concepts aren't that deep. I don't know why it took till Newton to figure it out. Actually, Archimedes figured out calculus 1,400 years before Newton did. But back then, the number zero wasn't allowed to be thought about because it was sacrilegious, because the number zero represents the void. There shouldn't be anything such as void because God is everywhere and is everything. So like the idea of zero could be talked about. So Archimedes' calculus basically got, he just didn't share it, and all of his books on it got basically written over by monks, Christian monks. That's how he found out in the early 2000s that he actually did discover calculus. They had some prayer books written by monks, and they used like fancy technology to see what was behind what had, been painted over, and they found Archimedes' actual calculus. That means that we could have actually gone to the moon 1400 years sooner. It's all about the development of mathematics. That's what produces our technology. So, I mean, if we'd have been to the moon 1400 years earlier, I mean, right now we'd be like living in other galaxies, that or we'd be extinct, right? We'd already destroyed everything on the earth, one or the other. Either we'd succeeded at getting off the planet or not. This guy is not a polynomial, right? But it's just a square root function. What does the square root look like? The square root of x looks like this. All this is it's been stretched by a factor of 4 and moved to the right by 11. So it's been stretched and then moved over. Okay, fine. So we're looking at what happens when x approaches 9. Where is 9? Well, if I plug a 9 in here, 9 times 4 is what? 36 minus 11 is 25. The square root of 25 is just 5, right? So this thing is totally defined where you plug in that, right? There's no holes in this thing. It's not like doing any kind of weird stuff, it's not doing that or anything, right? It's just a smooth function. So these simple smooth functions, right? We're not looking at the endpoint over here, right? All you have to do is plug the 9 in and you get the square root of 25, which is 5, okay? So as long as it's a simple, beautiful function, and you're looking somewhere like over here where 9 is, 9, right? There's nothing weird going on. All you have to do is plug that in, and you're good to go. 11.1 here is pretty easy. They just keep giving us easy functions. I guess 11.2 is where they're gonna show us like issues. All right, now this guy, like obviously you can't plug in a -3 here. This thing's not defined there. Right, if I plugged in a -3, I would get a -3 over 0, which is just totally undefined. I'm not getting no 0 over 0. There's no way to factor the zeros out. But who cares about what happens at -3? We're looking at the limit as x approaches 5, right? So although this thing has an issue at -3, -3 isn't anywhere near 5. So over here at x equals 5, this function looks just fine, right? So all we have to do is plug the 5 in, right? If we plug the 5 in, we would get 5 over 5 plus 3. We're getting 5/8, right? I guess I could graph this. X over x plus 3. X divided by x plus 3. Boom. Okay. So you can see, let's get a snapshot of this. Now, boom. The whole point of this is like, hey, over here at x minus 3, there's a vertical asymptote. This thing's not defined there. Who gives a crap? We're interested over here, right? Over here, this is just a nice smooth line. So whatever it was, 5/8 or something, right? You're getting closer and closer to 5/8 as you approach 5. Does that make sense? All right. Usually we're not interested about what happens when x approaches 5, right? That's just kind of like a lame example. Usually we're interested in limits where things are messed up, Usually this is where the weird stuff happens. That's the interesting part of the function. So usually we're going to be looking at limits over here. So let's look at -3 while we're at it. If I'm approaching -3 from the left, this thing goes to positive infinity. If I'm looking at -3 from the right, I'm getting negative infinity, right? So whatever this function is, we'll see this in the next section. If I approach -3 from the left, I'm getting positive infinity. If I approach -3 from the right, I'm getting negative infinity. So we'll talk about one-sided limits, right, in the next section. If the left-hand limit and the right-hand limit are both the same, then we say the limit exists. Here, the limit doesn't exist. The limit from the left is infinity. The limit from the right is minus infinity. Again, that's for the next section. Rational limits. So a rational limit is basically, if they're talking about a polynomial divided by a polynomial. If f is a rational function, right? A rational function is like 2x squared plus 3x plus 1 over x minus 2. A polynomial over a polynomial is what we call a rational function, right? And I said polynomials are nice, beautiful functions. But when you put one over another one, you have to be careful, like, when is that 0? Okay. What are they saying? If f is a rational function and a is a real number, so x is approaching a, we're not going to look at limits where x turns into an imaginary number. That's like higher level complex number analysis stuff. So, such that f of a is defined. So if you do have something like this, if you can just plug in the a into the function, if you can just replace the x with a number and you get a number back, then that's all you have to do, right? So if we're not looking at where this thing turns into 0 on the bottom, right? If we're not looking there, then all you have to do is plug in a for x, right? It's like this example right here, right? It's totally fine over here. Just plug the 5 into the function. That's it, right? Because it's defined there. Here's a theorem. We put this in the notes. It's in an ugly vomit colored rectangle. I could have picked a better color than that, right? Like, what is that color? I would call it bleh. Question, answer. Yeah, for a lot of functions. If the function is continuous, if there's no holes in it, you know, if you have something like where there's a vertical asymptote, right, there's going to be issues there, right? Or if you have like a hole in the function where it jumps, there's going to be issues there, right? Mostly, but not completely. Remember, the very first example was one that was like this, right? It was like this. There was a hole in the function, right? So for that one, yeah, you could actually just plug in a, because this thing is approaching, right? It's not defined there. The function's not defined, but from the left and from the right, it's approaching the same value. I forget what it was, 2 or something. All right. So let's see if what is this? Yeah, if f and g are the same function near a, then the limits are the same. So let's say this is f, and let's say this is g, right? And this is a. So f and g are different, but right here at a, right, as you approach a from the left or from the right, both of these functions are going to the same value. So whatever this would be, I'll call it L, right? So if the functions are the same, really close to a, then the limits are going to be the same. It's the limit theorem. Okay, so here, this is a rational function, a polynomial over a polynomial. So it's some beautiful smooth function, except for at 2, right? So at 2, looks like there's a hole in this thing, right? I'm not sure what this looks like, right? But Oh, and look, they want to know about the limit as x approaches 2. Well, that's the problem point, right? This thing isn't defined there. But I could say this is the limit as x approaches 2. Let's see if we can factor this guy. Let's see, x squared, we need a -6 and a +1, so what, a +3 and a -2, okay? So you can see what's going on here, right? Right, if you plug in a 2 here, you're getting 0 over 0. And that's not the same thing as just dividing by 0. If you're getting 0 over 0, there's something going on. Like 3 divided by 0, that's just totally undefined. But 0 over 0, maybe this is like 0 times 2 over 0, and you can do this and be like, it's 2, right? So that's what we're looking at here. So you can see, like, if you plug a 2 in here, you're going to get a 5, right? So even though this thing is continuous everywhere except for at, is it 2? There's a hole in it, right? We're getting 5, right? This thing is approaching 5 from the left and from the right, okay? Even though it's not defined right at 2, this is one of those where it's continuous and beautiful everywhere else except for right at that point. So you can't just plug the 2 in because you're getting 0 over 0, right? So yeah, you can't just always just plug it in, right? But if you rewrite it and get rid of the 0 over the 0, then you can just plug it in, right? At that point, you can just plug it in. So we want to be able to factor out zeros, basically, whenever possible. We should be able, we got 5 minutes, we could finish this section. Assuming there isn't like 45 more examples. Let's see here. All right, here's another one. This is a rational function. So I need to factor it. Let's just do what they did. So if you factor this guy, you could see, you factor that, you get this stuff. You can see the x minus 1s go away, right? They're talking about when x approaches 1. If you plug in a 1 here, you're getting 0, right? In fact, you're getting a 0 over 0, right? If I plug the 1 in, I'm getting 0 over 0. So we factor it, get rid of the 0 over 0. Now, this guy, now you can just plug the 1 in, boop, boop, and you're going to get a -1/7, right? So this thing is approaching 0 over 0, but it's actually approaching -1/7 times 0 over 0 is what that's what it's doing, right? A little trickery, right? This is the basics of calculus here. We've got to get our limits down. Look at another example. All right, well, this is not a rational function. All right, square root of x, polynomials don't have 1/2 as exponents, right? But this guy looks something like this, and then this guy looks something like this, and if you divide them, you're going to get something that's continuous everywhere except for at 4, right? If I plug a 4 in, I'm getting 2 minus 2. I'm getting a 0 over 0, right? Is what I'm getting. So I need to be able to factor that guy. And we can do that. I guess there's going to be a whole lot more. Well, we'll finish this example and then we'll have to pick up here. So here's an algebra trick here. Hopefully y'all can read. Can y'all read that okay? So we're looking at this guy. We need to factor it, right? So when you see stuff like this square root, and there's no square roots down there, check out what they multiplied by. This is the number 1, right? But why would you pick the square root of x plus 2? When you see something like that and something like that, when you multiply those, the square root of x times the square root of x, that's just going to give us an x, right? And the -2 and the +2 is just going to give us a -4. And then the cross terms, we get a -2 root x and a +2 root x, and those cancel out. We're getting rid of those roots. The square root of x sucks, right? So that's a trick that we can do. They call them conjugates, right? The conjugate of this is that. And we call it that because when you multiply those, the square roots go away, right? The square root of x times the square root of x is just x, and then we have this minus 4. Now we do have this square root on the bottom, but who cares? This gave us what we needed to get rid of the problem. This was the 0 over the 0. All right, so that's an algebra trick. When you see stuff like this, you got to use the conjugate trick. So it's a new trick for y'all probably, something y'all probably haven't seen before. So once you do that, you get this guy, and well, you know, for this, you can just plug a 4 in. And so if you plug 4 in, you get 1 over 1/4, okay? So we're going to learn new algebra tricks that allow us to take this 0 over 0 and factor out the 0 over the 0, right? Because this is really 1/4 times 0 over 0, and we want to be able to do that. And the trick here is right there. For this particular type of expression, this is the trick. So now you got a new trick, all right? We'll pick up on this next time. All right, remember, do your My Math Lab, do your guided notes, and the written notes, okay?